so welcome to the first CG Lab Talk for this semester. Today we have an invited speaker, Ákos Maróy. He's the founder of a company called Aero Glass and a founder of a couple of other startup companies in the past. And he will talk about how augmented reality solutions can potentially be used in aircraft. In particular, he will report on head orientation measurement problems and solutions that he was looking at in the last past weeks, months, and so on. So that will be the focus of his talk.
Thank you. Thank you for inviting me here, and hopefully my presentation will be at least a little bit interesting. So I'll be talking, first I want to give you an overview about augmented reality with emphasis on smart glasses or head-mounted displays used in augmented reality. And then I'm going to talk about basically the challenges of making something happen in our context, which is an aviation context. So in terms of augmented reality, it's a buzzword. It's been around for 10 years now, at least, and everybody is very excited about it. And we all associate high-tech concepts with augmented reality, but actually it's a very basic thing. I can get this one. So this is actually an augmented reality setup. There are these signs here which will make people stop for no obvious reason. And this reason actually they are stopping because reality is augmented here, and there is something semantic added to this space which tells people to stop. This is not something that so if we have the same setup, but without these signs, then people would not stop for no reason. They would stop if they see danger, etc. But the reason they are behaving differently in this area is that because we have put something additional in here, which is beyond your regular course of action. So we have been doing this for quite a long time. This is a kind of a physical setup, but now, of course, the dream is that you can do this in a more technological way. And of course, the advantages would be that you can customize it, you can tailor it to the particular person or the particular time or the particular event. Of course, changing these signs takes a lot of time, so you can't really customize the experience. Now, of course, we have seen cell phone-based augmented reality for some time. And a few years ago, a lot of people were very excited that a new era has come, and then we will all be walking with cell phones in our hands and looking through a camera instead of looking at reality, and then doing all sorts of augmentations with it, which obviously doesn't work. And there's a zillion reasons why it doesn't. Of course, the usability angle is the most important one. Nobody will walk around except if you're a tourist. Nobody will walk around and look at reality through a camera and then display instead of looking at real reality. So this is just not useful. So of course, but the concept has been around in popular culture quite a lot. So I'm going to show you a series of video clips which kind of showcase how movie culture thought about it since, let's say, the 80s. Let's start with this one, which is not a real augmented reality sample, but it still kind of brings us back to the early 80s thinking. This is, of course, Blade Runner. Where they have flying cars, which is nice, which we don't. But what they have here as well is that they are trying to navigate through drawing the path in the air they want to navigate through. This really ties into Aero Glass itself. Fortunately, the light conditions are not the best, so but we'll see the, so here, you see the actual path that they want to fly through display. It's not an AR display because it's in a separate screen. The concept is that you can just draw your 3D path in front of you. It's kind of nice. And this building kind of reminds me of the Tyrell building in a way, so it's really interesting. Yeah, keeping with Western culture, so this is sometimes in the US they call augmented reality Terminator vision, and the reason is Terminator 2. So you can just see, this is the scene in Terminator 2 where he has to get some clothing, so he's looking at people and evaluating them based on clothing size. So he's going to find the ideal partner there. So he's the one. Nice boots. So this is kind of a popular part of depiction of how these things could be or how they want to be in terms of augmenting stuff. Now this is second part of the 80s, RoboCop. But what I want to show you, which is I think more interesting, this is I don't know if you know this anime series from Japan called Denno Koiru. And this really shows kids with smart glasses playing around with an augmented reality world where they're interacting with something that is totally non-existent, but it has a profound effect on their lives. So here is a small scene. This is episode 1. They're chasing something that's not there. Interesting. And incidentally, this dog is also an augmentation. This doesn't exist anymore. I think this is late 80s, early 90s. Yeah, you can look it up, and it's fun to watch. And I just want to wait for the end of this scene because they will also display virtual keyboards and all sorts of UI elements that are. So here the video cat is not there. And then this is her kind of sign. You can interact with that. Yeah, so it's been around, right, in terms of concept, but it never really materialized. Anyway, we're getting there. But what was Interestingly, what we saw before is that all of these humans or partially humans that had augmented reality, they had to be extended in some way. They had either, I mean, Terminator, he was kind of an android to start with. RoboCop was an android. These kids, they have these smart glasses on. Fortunately, not bolted into them, but it's kind of an add-on augmentation. But it seems that to augment reality, you have to augment the human first, and then that's how you get to the augmented reality angle. So currently, it's very exciting in terms of timing because there's a lot of glasses that are coming around, and then kind of this augmentation part, the visual augmentation part, seems to be happening at a very, very high pace with very promising results. Of course, everybody heard about Google Glass, which is a failed experiment by now, but which was very interesting. It had this kind of visuality. So I wouldn't actually call it an AR glass in the sense that you don't actually draw on reality, but you always have a kind of a small screen in your field of vision that helps you with giving you information that can be tied to where you are, which way you're looking at, who you are, whom you're interacting with, kind of thing. There's another, this is a Canadian company called Recon. They have struggled lately, so they didn't really catch on, but wanted to create something very similar. Their solution is also a partial display, not on the top right, but on the bottom right edge of your vision. There's Epson. In the US, it's funny they say Epson, the printer company. Although actually this is the same company as Seiko, who is doing watches. It's kind of a regular big Japanese company doing a Moverio line of glasses, which looks like, the experience looks like this in terms of field of vision. But actually it can do stereoscopic 3D, and it can display stuff on top of what you're seeing. There is a US startup called Space Glass. Let me show their kind of concept. They want to, so they are combining glasses with all sorts of sensors on top of the glasses, and their concept is that they want to have a whole UI experience where you can interact with the virtual things through your hands, including measuring the depth of the displayed things, and then you can, depending on the depth of your hands, you can kind of select what you want to play with. And so they do stereoscopic 3D, and then they measure the distance and the position of your hand and your hand gestures, and literally you can touch something where depending on the distance of your hand. It's very exciting prototypes that they are doing. There is a and this is one of their concept video. Well, it's not, it's beyond the concept video now, so they're doing heavy prototyping. The actual hardware is, the beta hardware is based on the Epson glasses and some additional sensors. But basically, this is what they are working towards. In the initial video, they had a guy design a rocket engine with his hands, which is very futuristic, of course. Yeah. Yeah, so this is basically what they are looking towards. And there's a manufacturer called Osterhout. This is a US military supplier, basically. This person, Osterhout, he was heavily involved in the original night vision novel technology development. And they are doing custom glasses, which are actually quite high quality. I brought it there so you guys can take a look So getting back to the user experience perspective, so this is a screenshot from the original Space Glass Meta video where the guy is literally putting together a rocket engine with his bare hands, and then he sits in his Tesla and he drives away. No, the other way, he drives away with a Tesla. It's very high tech. But from a user experience perspective, this is also actually not particularly convenient. And the reason is the same thing. It gives you gorilla hands. You have to hold up your hands. And interestingly, your hands are too thick. So when you want to use your fingers to pinpoint and stuff, especially if it's in the distance, you're going to end up pointing at a lot of things at the same time. So it's very difficult to actually select or touch or even reposition things because I mean the level of detail on this thing is huge. So if you want to be able to kind of select the level of detail you want to work with and select things, it's very difficult. So actually when you, so we are a member of the Space Glass Meta development, Pioneer development program, and so we do look at what their UX development efforts are, and they end up having the problem like, they can recognize my finger, they can recognize what my finger is overlaying, but then if it's 10 items, then what do I do? So then you end up actually having a list selection, which looks ugly because you have to scroll through a list. So this kind of dream that I can just naturally interact with something by, I don't know, my fingers. It's not. It's more difficult than normal. It's way not as easy, and it's also tiresome. I mean, the point that we are using the mouse is that because it's easy, that it's a lightweight device, so you can just move it around with little effort instead of pinpointing things in the air. So when it comes to augmented reality, one thing is of course that you imagine that you can display things in an AR manner, but displaying passively is just one part of the whole game. You want to be able to interact with these things, and it turns that this kind of naturally seeming concept of finger pointing is not as good as it seems. So of course, what can you do otherwise? So you can do voice, which a lot of companies are heavily doing. Like you get Siri in iPhone, you get voice recognition in Android. Google Glass had a voice interface to it. Sometimes it works, sometimes it's very cumbersome, especially in a social context when you're walking on the street and you look like an idiot because you're saying words into a machine. Or people are overhearing you, or there's a noisy background. Sometimes can be quite comfortable. You can extend your AR experience with wearable devices, which are also coming up. I was a Motorola 360. Which can give you these kind of opportunities to have inputs where the nature of the input is simple. Like you have to select from a list of items, or you just have to, OK or cancel, or you have to do some simple inputs like that. So you can keep on looking at whatever you want to look at. Maybe you highlight something by looking in the general direction of the particular object, but you can find select with a small movement on your watch, or you can just confirm your selection or confirm your interaction. There are several devices which are even smaller, which are like rings, which serve the same purpose. So it's not even a watch, it's a ring. Interestingly, this Osterhout glass, it comes built in with a ring like that. So this is how it looks. Or so you can like put this on your finger, and it has a small mouse pad and it has buttons. So if you look around, then you can just confirm your selection. You can interact with the item like that instead of interacting with the actual glass frame or trying to do something else. So at the end, you're going to end up with not a single item, which would be the head-mounted display, but you're really going to end up with a series of wearable devices scattered around yourself, which forms a small network, or a personal area network, as Inta used to call it. And basically, this whole combination or unity of these devices brings a single experience to you, and that's what you would probably be using more efficiently. Interestingly, this is how we act. This is actually more natural than just thinking about touching things, because these are all bodies anyway, all the time. It's not just my vision or my hearing or tactile feedback. It's usually a whole body experience. So and of course, Terminator was a complete body. RoboCop was a complete body too. So it wasn't just Terminator with his eyes looking funnily, but it was like a whole Android body. So this is probably where, from a total UX perspective, where it's been. Okay, so now for the second part of my presentation, and this really comes into what we're trying to do and what kind of issues we need to solve. As a starter, I want to show you our concept video, and this has been keeping playing. Right. So this is what Aero Glass wants to do. This is not where we're at right now. I mean, for people who don't fly, so these would be like, of course, this would be the airway you want to fly through, or your own flight route. These are the greens or navigation points. These are the actual airways that other people fly as well. This is traffic, like other aircraft in the area. These are airspaces, the things that you either need to avoid or you need to be inside of. And then this is basically your approach path to a particular airport. And that's where you want to land again. And then we have augmenting important communication navigation data on the edge of your vision. And taxi routes and which way to taxi, which is surprisingly difficult at large airports actually. Terrain avoidance, basically coloring terrain according to the level of danger that it poses. This is the airspace again, airspace. So this is what we are intending to do, basically having an augmented reality experience inside an aircraft cockpit. Yeah, but it's not as easy as it seems at first. Or, well, I thought it would be easier, let's put it that way. And actually, I personally thought that the technological challenges would be somewhere else than what we are talking. But this is not only what we want to do. I'll show you some other concepts that are around the yeah, let's look at this one. So for example, this is Jaguar. They have something they call the 360-degree urban windscreen concept. Which is, in principle, very similar to what we want to do. So see the augmentations here. So they want to turn the column visibility issue, because of more passive safety in the car, is actually visibility is being reduced because all the columns of the car get bigger, so that you don't actually see outside. If you sit in an early 80s or 70s car, the columns are much narrower. You actually have much better visibility. Or pillars. The same here. And this is kind of something we already know from gaming, the Follow Me car or the Ghost car concept. So this is something that we want to play with. But, yeah, it's nice touch timing for the red light navigation points. And it could make sense. I mean, you know, if you've been lost or given direction, turn a little bit right in a difficult intersection, you might not know which way.
Are they working on this, or is it just a?
It's a concept. It's a Or they have another one which is less useful. For everyday life, it's more like oh, you'll see. It's more like playing a racetrack. But so it's very much tied into racing games. So yeah, it's like Gran Turismo 5 in reality. Yeah, so it's interesting that this concept, I mean, we have seen these in games for years, but the intriguing part is that if you can really make this happen in reality, it really kicks ass, right? I mean, it's much better to. Well, of course, it's more dangerous too because you can break yourself on the racetrack, but it would be interesting. But actually, you can make some stuff safer too. Like here, all these cones are non-existent. And even in Aero Glass, we're thinking about doing obstacle courses or games up in a safe enough aviation. So, for example, we could have a race course, an acrobatic course like the Red Bull Air Race course is, let's say, 5,000 feet higher than ground. And then you won't hit anything if you actually fail. So those are possibilities which actually enhance safety. Okay, so let's look at what the actual challenges are. So be able to do AR that we are aiming to do, which is a bit different than doing your only computer vision or video recognition based AR. We need three things basically. We need to know where the person is, which way he's looking at, and we need to draw basically a virtual globe based on these parameters. Let's start with the virtual globe part. So this is basically Google Earth in an Android. I'm saying Android because these devices typically run Android, so that's basically target platform. Actually, Google Earth does run on Android, so you can start with that. But there are other engines that do the same. Here, I'm not going to elaborate on this too much. It's not that simple as it thinks, but it's not unsolvable. So basically, you start with a WGSA4 ellipsoid model of the Earth, and incidentally, this is the model that the GPS system uses to tell you where you are as well. So that there is an alignment there, which is good. Then, because you want to display things in a georeferenced basis, so whatever you want to display, basically have a geo coordinate for it, which is based on the elevation is based on either this ellipsoid model or elevation in relation to the mean sea level. There is a problem that the mean sea level is different everywhere, so we have to do a geoid correction for that. So this is how the actual thing looks like. So you have like this spherical model, which is which is supposed to be simple, and then you have the actual sphere of the globe, which is different than your spherical model, and then because of the gravitational differences, the mean sea level is different everywhere. So you have to do this kind of correction. As you see that the geoid model would be here, but the actual sea is there, so you have to correct for this. Good thing is that there has been these surveys, and it's basically, you will end up with a huge bitmap, which is a correction bitmap, and you just have some variation. And then you have a lot of OpenGL rendering challenges, and these really come from the fact that OpenGL is created for gaming. Usually the gaming scenes are small in terms of, you know, maybe 10 kilometers, but that's already a big scene, usually less. I mean, I'm saying kilometers because usually it's a human who is running around, so that's kind of big. So you end up, but when you do augmented reality like for aviation, sometimes the far distance that you have to see through is 500 miles. And the problem is then that the short cutoff and the distant cutoff is very far from each other, and then you're going to end up with a lot of issues of floating point precision problems and that kind of stuff. So there's some challenges there, but this can be solved, so it's fine. They will even run on the Android device, so that's good. The next thing is position, so you need to know where you are. For an aviation context, GPS is good enough. I mean, it's not totally precise, so for example, for the Jaguar urban car driving concept, you have to do better. Especially in the city, sometimes you don't even get a GPS lock if there's tall buildings around you. But of course, the good news for that solution is that the car-based GPS navigation has been around for some time. It has been fine-tuned. It works quite well. But for us, we are in the air. There is no obstacles to see a lot of GPS satellites. And with an aircraft, you're typically not flying less than 100 kilometers an hour. So a positional error of 10 meters plus minus when you're flying at 100 kilometers an hour is kind of okay, especially if the things you're looking at are a bit far. So of course, when you're about to land and you're basically whenever you're getting closer to the ground, you don't need more precision. So that's something you always have to work on. And as soon as you're on the ground, basically you can use the same tricks that car navigation or pedestrian navigation applications use, that you assume that you're on the ground, so that gives you a level of precision that you can precision out. But the position is mostly covered. And then the issue at hand, and this is something that we've been struggling with a little bit, is the orientation, telling which way the person is looking. Naively, of course, one would think that an IMU or inertial measurement unit is good enough. Well, it's not really. Of course, everybody is very happy that now all cell phones, they have these gyroscopes and magnetometers and accelerometers because these chips have become cheap. And they are useful for a lot of use cases. Like they can count your steps and they can generally tell if it's a portrait or landscape picture, that kind of thing. But for our precision, it's not good enough. Usually, this is the quality of a sensor that's put inside a regular cell phone. And the same thing is put inside the smart glasses. This costs around $10, maybe $15, but it drifts very heavily. You can try to buy your way out of this problem. Unfortunately, that's not true. You can go quite a number of orders of magnitude more accurate for, say, a tenfold price increase. Still not good enough. That's like 20 degrees per hour is just too much. And then if you really want to go for higher price, then it's still not going to be too good enough. I mean, 5 degrees per hour is still too much. Too much in terms of for what? Let's say a person might fly 4 hours on one shot. So that would mean a 20 degree inaccuracy at the end of his flight for $1,000. So of course, this is kind of the raw measurement. So there's a lot of algorithmic optimization to be had. You can counter the drift in a lot of ways. This is something everybody does. Unfortunately, in our case, a lot of the assumptions that are used for countering drift are not applicable. For example, if you're sitting at a desk, you can use the accelerometer quite well because it's usually going to point towards the center of the Earth. And that's kind of a good anchor to use. But when you're flying in the air, this is not true. Usually, when you're doing coordinated flights, the accelerometer will point to the bottom of the aircraft, even if it's upside down. So you can't really use it to compensate for the vertical aspect of your arrows. And similarly, if you're sitting in a single place, usually the magnetometer is going to be imprecise, but at some point it might help you in the aircraft. So it's kind of so pretty much you're left with the gyro. You can't really use other sources of compensation based on the IMU, and it's not just not going to be good enough. And by good enough, I mean like if you have a 1 degree error, then it brings you a mile off in a 60-mile distance. So the mile is just too much. So one of the solutions is that you want to basically split this problem into two. One is that you assume that you know your vehicle's orientation, because it seems to know because there are these instruments inside which tell you where your aircraft is looking at. So that's kind of a good starting point. And then basically at kind of the other part of the problem is that then you want to tell, because you're not always looking forward, you want to be able to tell which way your head is turned in relation to the aircraft itself, and then you add these two together and you should be all set. It's kind of the theory. And indeed this has been done, and this is how these issues are approached. One is a magnetic field change measurement approach, where you create a magnetic field which has a certain shape, and then you measure your turn in relation to this magnetic field. This is something that is, I'll show later, this is something which is being actually used by Rockwell Collins in an aircraft helmet. The challenges with this are, it's of course price. The other one is calibration. So the magnetic field inside an aircraft is very peculiar, and also it changes whenever you turn on and off things. So they have a very extensive calibration process per aircraft when they use this. And then you can use a number of optical tracking approaches. One could be a markerless tracking, where you try to, of course, these glasses, they have cameras built in already, so they're not looking forward. There's some overlap between what you see and what the camera sees. It's not a one-on-one overlap. So what you could do is you could do markerless tracking and try to identify significant features and then do tracking based on that. And you can track markers. That's another approach. And you can, visual markers, and then you can actively track. You can track active markers as well, like infrared lights and stuff. Let's go through all these possibilities. So one thing that you can do is kind of just use the camera built inside these glasses, and either use a SLAM or a marker tracking approach. Here the challenge lies within here. So the challenge is twofold. The field of view of these cameras is not really wide, and even with the rapid head movement, so you have to build up this map, and then you have to work with that. And the problem is, as soon as you start to look outside the window, there is nothing to track, because you're looking at the mountains and whatnot. So we basically lost sight of the aircraft. So that's a problem there. So it's two issues here: the narrow field of view, and you're not always looking at the aircraft. There is another approach which looks very odd in the beginning, but actually this is the most promising one. Is kind of you're looking upwards on the ceiling with a camera, and you're tracking things above your head. The good news with this one is that basically you're going to be tracking the same area all the time. because of the nature of the head movement, usually turn your head around. It's very unusual in a vehicle like an aircraft to look down or to slant your head like this. Sometimes you do, but you only do it for short amounts of time. At the end of the day, you're going to end up looking below level. So this is something which is very promising. And then there is a third approach, which is called outside in, where you have something that is looking at your head, and then you have to have something on your head that can be tracked. And this is also not prone to you looking around, and it might be actually very promising way to go forward. The kind of the downside of this approach is that this means that instead of just having something on your head, you have to have an active component outside of your system. And you have to have a kind of a communication thing going on in between, which makes everything more complex. So let's look at what others have done or what people have done about this. So this is Rockwell Collins, huge US military supplier, and they are shipping a helmet into the famous F-35 aircraft, which has been the most successful aircraft development story in Western military aviation history. Not really, no. Anyway, they are the ones who are using this magnetic resonance change tracking system. The tracking manufacturer is called IMUs. You can look it up. They also use this in motion tracking for movies, this kind of an approach. And the challenges it has is really these calibration challenges and the changes in the nature of the magnetic field. Oculus Rift, I'm sure you all know. Interestingly, it's also using a tracking approach with a new development kit. It's not visible if you just look at the DK2 case, but it's full of infrared LEDs that shine through the black case. Let me show how, and then you have an external camera, which is an infrared camera. And they are using this camera to track your head orientation. So they also figured that even in a use case such as the Oculus Rift, they're sitting in a chair and not moving, the IMU is never going to be enough. How this works is that each of these LEDs is blinking a 10-digit binary pattern, 10 binary digits. So each of the LEDs is identifying itself by this blinking pattern. So by looking at 10 frames, then you know which LED is where. The system is built such that there is a cable between your headset and the camera, and the headset is triggering the frame shots of the camera. So so they set the new blinking pattern, then they trigger a shot in the camera, new blinking shot. So it's all synced up. So that's why it's kind of accurate. It does, I think, 30 frames per second, so it needs 10 frames per identifying the LED, so it has like an update 3 times a second. Let me show how it works. So this is a demo. This has been reverse engineered by German guy at California University, and basically this is the final tracking solution you see here. So the numbers are the identifiers of the LEDs. The 3D frame is the actual reconstruction of the Oculus Rift DK2 headset, and the green things are the LED blinking patterns. And the good news about this one is that you Google it up, it's open source, so you can download it and you can play around with it yourself. The reverse engineered version. So that's how Oculus does it, basically. So they use the IMU inside, and then they use this tracking algorithm externally. This also gives them the possibility to have not just orientation but motion. So with the DK2 you can have sets where if you lean forward or lean backwards, the user experience can change. So it's a more immersive environment. Yeah, maybe. So that's like the same thing on the side. And here you show if you move it rapidly, then the tracking of course is lost, because it needs the 10 frames to identify the LEDs. So then you only see the green dots, but you don't know which one is which. And then there is another solution, which is this company is called Thales Visionics, although it has been a different company, and Thales bought them, I think, last year or something like that. And this is the whole system, but basically the tracker is not this part, but looks at this one. So basically it's kind of something that you bolt on a helmet. And it has an upward-facing camera, and it's tracking markers above the actual person's head. And let me show you there. Basically, a demo they did a year ago in a car. Very environmentally conscious people. They are driving a Toyota Prius, and basically this is their. So this is how their system looks like. This is going to end up looking upwards. So you have to imagine a helmet, it's on the side of the helmet when you come out. And this is the markers they have on the sunroof of the Prius. And each marker is identifiable separately by the signature of the marker. And then they are using this simple webcam to record whatever gets shown there. So what they do in the beginning, it's called bore sighting. So this is an actual rifle bore sight. And so they look into this in a level manner, and this is how they align the visual tracking with the vehicle. Because of course you add the visual orientation to the vehicle's orientation, that's how you come up with the final orientation. And then here, this is the interesting part of the video. So this is a tower, and they're going to continue to draw a line on the tower in a quite precise manner. Of course, this is your horizon. Here comes your tower again. And here they are cheating somewhat because they are on the ground, so they are forcing themselves to be on the ground, so their position info is a bit more accurate than airborne. But this way, for example, they can draw this path, which is just the road info taken from OpenStreetMap, and they are going on the road. You see that this is the edge of their display, so this is kind of the field of view of the display. So as opposed to the concept in the Jaguar video, this is something that has, this is about 1 year old, this video. So this is reality. So here is your tower again. At the end of the day, this system claims to have a precision of 0.3 degrees when the visual tracking works, and 0.6 degrees per minute drift if it doesn't work. That's what they claim. So basically, in terms of, so we have 3 challenges for the vehicle-based or aircraft-based augmented reality. One, and the third one with the orientation, the conclusion is that it seems that the outside-in approach, which is used by Oculus, is working, and the kind of the ceiling-based approach that you look upwards and track markers on the ceiling, these are working. And the all light conditions, so you want this to work at night and day at any time. is solved by infrared illumination and infrared markers. This is in both cases. This is how this is. And then you can get kind of a precision about. In the case of Thales, it's 0.3 degrees. Oculus is a bit less accurate, and they only get updates 3 times a second from the tracking solution. But then, so you get a solution which is kind of accurate, so it can be accurate. You add some inaccuracy from the vehicle orientation as well, and you get to somewhere between 1 and 2 degrees, which is good for a lot of use cases. So you can basically use this in a lot of cases. Well, thank you.
Yeah, thank you very much. Any questions?
Yes. My first question would be, you said for the positioning you completely rely on GPS. Are there any plans to use some computer vision camera tracking? So I can imagine that if you have like other aircrafts that fly around which are very close to you, that this would work to use the camera as well, maybe in a hybrid fashion to use GPS and the camera.
In short, no. Other people have tried and it doesn't work. So basically the problem with aviation is that for collision avoidance, aircraft collision avoidance, the speeds are so big and the camera and the aircraft cross sections are so narrow that to visually identify an aircraft, it will give you a time space about 3 seconds for evasion, maybe 4. Mm-hmm. So it's just not enough. It literally will be hunting for pixels until it's too late. So what they do instead is that they have active systems which are radio transmission-based systems for collision avoidance purposes. Depending on the use case, the gliders use a different technology. It's called FLAR. The motor aircraft, especially commercial aircraft, they use something called ADS-B. Basically what they do is, at the end of the day, each aircraft is broadcasting their own position, and then there's receivers in the other aircraft, and they can basically determine if there is a danger factor lying around. And then they would either, in the case of the gliders, they would just show you a generic direction, like you should be looking to the right-ish kind of display. In the case of commercial aircraft, they actually have active avoidance systems where the aircraft is issuing a command to the pilot at some point, saying that you need to climb or descend to avoid the collision. But these are all based on each aircraft measuring their own position based on the GPS, and then transmitting or broadcasting this position data to others. The visual recognition is just it's just not good enough. It will give you not enough time, space to react.
Okay, and the second question that I have is a more general one, so it's not technical. Usually you have a lot of security regulations when you fly, and aren't there any issues that the technology can clutter your scene so that you can't see what's actually going on in reality anymore? And that this could be an issue. I mean, this last video that you have shown with this path, when a car was driving, this was very, cluttering what you're seeing. And could this be an issue? Do you need a certification that people can actually use it?
Yes, it could be an issue. No, you do not need a certification. So how it works is that as long as a tool is not claiming to be a primary source of navigation. So there's this term they use in aviation, primary source of navigation. So as long as you're not claiming to be something like that, you don't need to have a certification on your own. This is how a lot of tablet-based navigation solutions work, that it's kind of a helping device. Because on the other hand, nobody is stopping you from doing things that you think is helpful to you. So like you can have notes on a piece of paper if that's helpful, or you can have an iPad with an app on it if you think that's helpful for your safety or flight. So nobody's stopping you trying things out. Yes. But of course you cannot claim these devices to be your primary source of navigation because they are not.
But I mean, people will rely on it, right? So if technology works well, they will rely on it, and if there is an issue, they could sue the company.
Yeah, so let me separate two different issues. One issue is, of course, liability. Like, if there is an accident is the manufacturer of that or the writer of the particular iPad application or Apple, the iPad manufacturer, are they going to be liable? No, they are not, because it's not a primary source of navigation. That's how it's being sold. On the other hand, yes, people rely on it? Yes, they do. People use iPad or tablet-based nav apps. If they use them, they use it 99% of the time for the people who use it. Because it's much more useful than having a paper map and having to cross-reference, like, you look at a village and does it have a church tower? Yes, in the map it does. That one doesn't. Literally, this is how it's happened. So this is how visual navigation, this is how it's supposed to happen. Or is there a river going through the village? No, it's a different village. So instead of that, you just look at the chart and you say, oh, yes, there's something to the left, it's called this and that, and then you're fine. Of course, this is something you want to do. So in our case, you'll be able to look at the village and we will just put a label. So if this is useful, of course, you're going to use it. You're going to use it 99% of the time. But if you are in doubt, or if the application is in doubt, then the application should turn off. And it should just say, it doesn't matter. And then you should fall back to your proven and actually approved method of navigation, which would be a paper map or something, or your instruments. And having said this, that it should turn off, this is actually a legal requirement. So the regulation says that you should not show serious and misleading information. So if you would be showing totally different cities and totally different attitudes and whatnot, then you are misleading the person. So then you could be liable to some extent. And the cluttering issue is a usability issue. So that's something that we have to work on quite consciously. That you only want to show things that are relevant at that particular time point. Or you would want to have the user turn off everything if they don't need it.
One more question regarding the
speak up.
What?
You have to speak up.
Okay. One more question regarding the outside-in tracking approach. You showed that it's Oculus Rift development kit 2. But Oculus Rift is a virtual reality thing, so you have the screens directly in front of your eyes, and it's tracking somehow the back of the screen with the lights. But if you would want to use it, you need somehow an AR approach. And where do you want to position the lights? Or I don't know. So how you would use this?
As I said, that approach has a lot of practical issues for our use case. One of them is that we would need to have an external camera which has to have its own battery power source, because you cannot use cabling. It needs to have a wireless data connection of some sort, so more battery again. Most probably it would need to do the actual recognition algorithm, run it on its own, because then the bandwidth usage is lower if it can just emit the orientation data instead of emitting the actual frames that you would do it somewhere else. So you end up with a very special kind of GoPro setup, basically, that does all this tracking and everything else for you. So that's one part of the difficulty. The other part of the difficulty is that you need to put sufficient amount of markers on the user's head. On the Oculus Rift DK2, there's 40 different markers on the side, on the top, bottom, in the front. And there they're using the PMP algorithm to determine the orientation, which means that they assume the relative position of the markers at manufacturing time. This is why it's a hard shell, so it's easy for them to do. For us, this would be very difficult because our users don't use helmet. Would be wonderful because but our users, they don't use helmets, right? The glass frame itself that we use is rigid, but you don't want to put a lot of weight in it, and most probably you can't put enough LEDs on it, even if you put an extra frame onto it. You could use a special kind of hat of sorts, but if it's not if it's not a hard hat, then you lose the requirement that you know that the relative positions of the LEDs are fixed, because the shape of the head is going to follow the shape of the guy's head and everything. So that's also a problem. You could use the headset frame, because the aviators, they use headsets. But then you might not be sure that you have enough LEDs there either. So it's a problematic solution in our case. On the other hand, when you can actually meet these requirements, it works quite well.
The problem that I see with this is not only the number of LEDs that you need, but they also, to make sure that you can track this correctly, they also need to be non-coplanar, which means you need to have these LEDs distributed from different planes of the frame, not only on one plane. It would not work if this is actually only on one plane.
Yeah.
So on the one hand side, you have the problem that you need many of them to track precise, and they have to be distributed in a non-coplanar way to get precise tracking. And then, of course, you have all the additional issues like more weight, power that you need to.
And you need the time synchronization, which is done with the cable in the Oculus Rift setup. But here we would need something that is. But if it's like 30 frames per second, then you need to be in between changing the LED setup, so that patterns, we have to be sure that the frame is taken right there. So you need something which is maybe a 300 hertz or better time sync between these two devices, which is a wireless time sync. It needs to be wireless. So quite a few challenges.
But besides like the performance and the weight issue and the electricity issue, I think the biggest problem is still that you probably cannot distribute these LEDs on an AR glass in a sufficiently non-coplanar way without running into also occlusion problems. There's one camera that can see only a few LEDs from a particular head rotation. You have to see more from different planes to get the tracking done. So
so this is like Osterhout glass. You might want to pass it around.
You end up basically having more cameras at the end to avoid occlusion.
Mm-hmm. So this is how like one of the manufacturer's glasses look like. So this one has everything inside the glass. This has a quad-core CPU. The display is 720p each eye. So this is quite, in terms of specs, this is quite good. And it feels heavy, but it's actually quite not that uncomfortable to wear. But this is where you would want to have on a place where your LEDs on. It's the kind of the surface area, isn't it?
Any more questions?
What I think,
okay. I can repeat the question.
Yeah. What I think is more is interesting is to augment reality where you can't see anything, especially at night. All the videos are always at daytime. So I'm seeing things. What I like. I mean, I don't know much about flying, but for driving a car, it could be very interesting to see at night. For example, people walking around, because you often have the situation where you see people very late, and then you have to brake fast or something like that. Is there any reason why all these things don't show, for example, the concepts at night? It would be more interesting, I think.
So the question is why do the concept videos are always shot at daytime? I think that it's for cinematic purposes, really, because at night you definitely don't see anything, so it's difficult to showcase. And then you have to take, I mean, except the Jaguar video, the other one was really taken with a webcam by the dev team. So it wasn't really an orchestrated effort to create a nice video. But you're very right. I mean, the real use cases of these solutions is when you don't see anything. When you fly in a cloud, you don't see, literally don't see. You see white clouds, or in the night it's even worse because the strobe light of your own aircraft is going to make you throw up, because it's blinking back from the cloud, and the prop movement will make you swirl. And blah. So it's really terrible, and you don't see anything. And that's when these solutions really help, right? And that's the whole point. But it's difficult to showcase in a concept video that you're showing something that's there which you don't see, so you can't prove that you're showing something that's there, right? So you have to. From a cinematic perspective, you have to show it and hide it, show it and hide it. So this is what they did with the tower behind the building, and then coming out from behind the building, so that then you would continuously tracking the same tower, either when you see it or not. But yeah, it's totally valid point. During the night, it's very much helpful. Of course, with nighttime, you have to be careful with the contrast. So you have to tone down the amount of light that you use, the strength of light at the displays, because otherwise the person is really not going to see anything even if you saw it without the glasses, because of the lack of contrast that you would have at that time. Usually what you do in an aircraft, and also what you do in a car, is that you dim all the lights down inside the vehicle, so you can see the outside.
I was always thinking about this virtual windscreen where I can see people walking around at night
Sure.
and see, for example, when it's raining, you can hardly see the lights on the street, so this is very difficult sometimes.
Yeah, so that would be a very good use case.
More questions? My final question would be, what does your current software support at the moment compared to the concept video? What does work? Leaving out the tracking problem for now. So assuming the tracking problem would be solved, what can we do with your software?
So currently what we have is basically a read-only or a passive navigation aid. So that means that if you put our solution or turn your solution on, then we are able to show you all the airports globally, all the navigation points, cities, villages, that's also global coverage. We can show runways, we can show airways, and also interestingly, that's kind of a bit of an overshoot, but basically ILS approach cones for ILS approaches, which is an instrumental approach procedure part, but it's just kind of we did a quick demo on how to visualize it. I think it was easier. So basically, the current solution, we can be kind of an augmented reality map that shows you where things are. Currently, we don't have support for your own flight plan or for own intended route. You cannot select the waypoint and say, I want to fly there, show me the direction, how I want to fly there. We don't have airspaces now, so that's something that we need to add. We don't have terrain avoidance now, that's something we will need to add. We do have traffic, so if we have ADS-B reception, then we can show the other aircraft which are in the area. We almost have floor-based traffic for gliders, but it's almost there, but not there yet. So we have a lot of things which are basically visualizing data that is not changeable by you. So there's no interaction possibility at the point, but it's also already very useful data that you can rely on. And then, of course, the future path is to finish the visualizations that we don't have yet, like the airspaces, terrain avoidance. We want to do IFR procedures, departure, arrival, etc. And then we want to have interaction, so you could be able to specify your intended flight plan, change that flight plan on the go as you receive more clearances, or you just change your mind, and be able to highlight things and select them. Also in the concept video, we saw all the additional data about the airport and the edge of the vision, so we're able to basically interact with things in a manner. So you pinpoint an airport, and then you get all the communication frequencies and whatnot. And our intention is that you should be able to tune your radio based on this data. Mm-hmm. So you should, instead of hand tuning on the cockpit instrument, you should be able to say, I want to talk to that airport. Mm-hmm. And then your frequency is tuned into the radio when you're talking to them. So that's kind of the vision that we want to have, that eventually the actual cockpit would become less and less important, because you will be interacting with your environment as you see it around. This is why I was focusing very much on the user experience angle, because we think that this looks funny that you pinpoint that stuff, but if you're in a turbulent environment and your aircraft is shaking and your pointing is not going to be precise enough, and you don't want to mess time with no, not that one, the other one. So then you need more reliable ways of selecting things. But your vision is one good way of, your orientation is one good way of highlighting certain aspects, and you just select them and then you feed them back into the aircraft.
I mean, instead of pinpointing with your hand or with your finger, you could only just look at a particular thing and then trigger something.
Exactly. So basically how this would work, and this is something that's what they also work on in the Spaceless Meta, the UX API, is that gazing at something, so you keep on looking at it for some seconds, then most probably you want to do something with that. So then it already triggers a UI event, and then you can either confirm, or you can just say, no, not that one, but the other one beside it. So you can do like these small side selection things. Mm-hmm. And that's quite efficient. So you look into the generic direction and you say, okay, one to the right, click, and then you've selected something. And then this kind of a user experience. And also we want to be able to show, for example, when it comes to traffic or other kind of immediate danger, then what we want to do is we want to turn the pilot's head. So basically tell him, look to the right, up there, instead of telling him that at 3 o'clock there is something. So to turn his attention to either the source of danger or the next action point. If you identify that he's an approach but his gear is not out, then you want to tell him there is your gear release button, you have to activate it. That's a problem. So these kind of help to this.
Seems to be a very promising approach if the basics work, the basic technology work, and tracking is probably one of them. Any more questions? And thank you again.
Thank you.